Bismillahirrahmanirrahim. So let us start. So this is our session 5, and we will be designing the combined footing for 3-story commercial building in this session. And these are the contents, which the size of the footing and thickness of the footing will be discussed, and then punching check, and at the last there will be our reinforcement design for the combined footing. So before going into the design of the footing, let us check the model which we will be exporting from ETAB to the SAFE, that it is now a 3-story building and its configuration is totally different from the previous one, right? So you can see it consists of 4 bays in 5 bays in this direction and 4 bay in the Y direction, and the loads are the same for the practical point of view. As I show you or display the load which I assigned to it. So these are the loads, live load, which is 40 in case of the residential and purposes for the apartments, for the shops. And this is the SDL, which is 30 for the 3 inches tiles or other terrazzo floors. These are the superimposed data, right? So this superstructure has been designed and modeled. Now the our part here is to design the combined footing for this. You can also design the isolated footing or strap footing or raft for it, but for the learning purpose and for the understanding, we will go towards the combined footing, right? So the first step is to check the reaction on the basis of the service load combo, and check this. This is the combination. This is the service combo. I check on this FZ, and it will show me the service load combo reaction of the columns. And then you have to again, this is the engineer choice. If you want to make combined footing for the 2 columns, then you have to combine the reaction of these 2, and then you have to calculate the required area for the safely transferring of the loads to the foundation, right? So it's your choice. If you want to make a strip footing, you can also do that. For example, if you want to make a strip footing for from this end to this end, then the procedure for this is to sum all of the reaction of this line. This will be the total load, and then you have to select the actually calculate the length of this strip that you have. This is the length, this is available length, and this is the total load is available. And then you have to sum all of these load and divide these load by the length into the allowable bearing capacity. Then you will get the weight of the strip, right? For in this session, we will be going towards the combined footing, in which we will be combining these two columns to make a combined footing for these 2 columns, right? So we will select the maximum values from the 2 columns, that is the for the service load combo. Let us select the 130, 193, and 189, and this is the maximum for the interior columns, and we will sum up these 2, and then we will select strip width, and we will calculate the length of this combined footing, right? So now we have selected this FZ 193 and 189 for the interior, and then we will select 131 and 90 for the exterior, because these are the same, these are the mirror one, right? So let us go towards the presentation again. And these shallow foundation definition as per ACI code is the same for all of the footing, that we have to calculate the area using the unfactored load, which is the service load, right? So this is the computation of the area in which you have to compute the total maximum service load on 2 columns or more columns if you wish to combine more columns in the combined footing, right? So from ETABs, we have selected P1 is equal to 194, that was 193, so we have run out into 194, and the other one is 189, we have run out into 190. For the exterior, we have selected 2 columns, which is 131 and 90, right? The bearing capacity is same from the previous case, that is 4.63 KSF, right? So the important step in this is to calculate the area for the combined footing, is that if we keep the width 5 feet for the combined footing, then you have to calculate the length of the combined footing. And how do we calculate that? The procedure for this is to sum the total load of the two columns, which is P1 and P2, 194 plus 190, and then divide that by the selected width, which is 5 feet, into the allowable bearing capacity, and it will give you the value in feet, which is equal to 16.5 feet, right? So the dimension for the combined footing comes out to be 5 width and length is 16.5. Similarly, for the exterior one, if we sum up all of the reaction for the exterior, which is 131 plus 90, and divide that by the selected strip, you can change the strip as per your requirement and multiply with the allowable bearing capacity, and you will get the 10 feet. But we will take L2 as 14 feet. And why you do that, I will show you in this in a minute. For the interior, we have the combined footing 5 feet cross 16.5. And for the exterior, we have 5 feet cross 14 feet. So let us go towards the ETAB again. So the center to center distance between the column is 12 feet, right? So for these two columns, the distance is 12. And if I go beyond 2 feet, 2 feet 3 inches from this point and 2 feet 3 inches from this point, it will become 16.5. So we will draw our footing in 5 in this direction. This is the width and this is the length, which is the 16.5, right? For the exterior, the length that came from the calculation was 10, but the center to center distance is 12. So we have selected 14 for the purpose to combine these footing. So from this point to this point, this is 12. And if we add 2 feet, it will become 14. So this is our, this will be our dimension for the combined footing. It will be 14 in this direction and 5 in this direction. So this will be the combined footing, right? So how do we model that? So let us unlock this, and you have to click on this draw joint objects, and you have to draw the joints to draw the combined footing. In X direction, that is 24 feet, 24 inches means 2 feet and 3 inches, so it will be 27 inches. And this is the in X direction, for example, this is the point. So you want to go 27 inches in this direction, but the strip width is 5, and if you divide by 2, it will comes out to be 30 inches, which is the 2.5 feet. So in Y, we will add 30 inches. So these both are the positive direction. So if you click on this in here, so this is the point of the combined footing. This is the first point. Now make it minus 30, right? So this is the another point, and now keeping that minus point, keep that 27 is minus, so it will be another point, and keep that minus and keep this as positive. So this is the third point, right? So these are the dimension for the combined footing, and you have to draw the footing. Let us draw it like this, and then this is the, you can see that the width is 5 feet and the length is 16.5 feet, which we have calculated, right? So in this way, you will model your footing, and you have to replicate that by using the replicate command and select 2 points. You can select 2 points, and again, similar procedure for all of the footing will be followed, right? So this is how you model the combined footing in ETAB. Now the last one is for the exterior one, that we have to model the footing for the exterior sides. And this is the, for example, this is the boundary of the plot. You cannot go beyond this point and from this point, but at the start you have the authority, or you can go beyond this point. So these will be at the center, and the outer edges will be on the edges, right? So for this, you have to again draw the joint objects. So for this strip is 5 feet, so you have to click on the X direction, and it will be the positive direction. It is 60 inches for 5 feet, and this is the point. And for this point, this is the 60 inches, but it is beyond 2 feet, so we have to apply minus 24 inches and click on this point, right? So this is the point for the combined footing for the exterior, and you have to now draw your combined footing, right? So this is how you will model your combined footing, and this is the typical procedure which I have shown to you. You can use this with more and more practice, so it will become more easy, right? To save time, I have already modeled this, right? So this is the combined footing, in which these are the two columns, these are the two, but there is a one column left, so you have to draw the isolated footing for it, and how we do that and how we calculate the area for it, which we have already covered in the isolated footing design, right? So this time I haven't assigned any springs to this footing in ETABs, because you will be assigning springs and defining in SAFE, so you can get to know how you define and assign the springs in SAFE. All you have to do, again, you have to go to export story, SAFE story, and then you have to select the base and select the export and all of the load combination and load cases, and click on OK. And then you have to again go to the desired folder, and you have to save the model for the to be imported in the SAFE like this. For example, you have to import it like this, and you have to give some name to it, and you have to save it. Now again, you have to go to the SAFE, and you have to import that file as a story file, SAFE story file. This is the file, and it will be imported. Now the next step is to define the soil property for it, right? So this is, we have calculated the area. The next is the thickness of the footing, in which we have already discussed that the ACI recommend to use the minimum thickness 6 inches, but in our case we would use 18 inches thickness for the 3-story commercial building, right? The next step is to define the subgrade modulus, and this is the same which I have explained in the isolated footing, and the bearing capacity is the same. So the stiffness for the spring to represent the soil comes out to be 166,625 pounds per cubic feet, right? So this is the same. The next is the to export to SAFE is F2K file, which we have done, and then confirm the loads and run the analysis, right? And then check the punching check, etc. So now the next step is to define the subgrade modulus. You have to go to the soil subgrade properties, and you have to add new property, and you have to write the subgrade value, which is 166, right? And this is 622. And you have to click on OK. So this is the soil 2, and you can write the bearing capacity, for example, is 2.5, 2.1 TSF. So you can assign it easily. And then you have to select all the floors and go to the assign and click on the support data, the soil properties, and we have to click the desired properties which want to assign, and click on OK. Now the soil has been assigned to the footing, right? The next part is to define the slab property, and this is already being defined in ETAB. You can also change it. Some students ask about the slab or the mat or the footing. These are the same, because the ETAB or SAFE designed it as a two-way slab, all of these, right? So this is 18 inches. So now it is ready to run, right? To save the time, I've already run the analysis, right? So this is the same model, and if I click on the first punching check, you can see there is no issue in the interior columns, but there is a big issue in the exterior, right? Because these are there at the edges, and at the mid there is no issue, because the 18 inches thickness of the footing is enough to control the punching demand, right? So the first solution is to combine all of these external footing to make it as a strip, but still it will not work because it is 3 stories and it is not recommended to combine this, because if you combine this will come 3 or 2, but still there is an issue. But the best part is to provide a straight beam in this, because it will become economical as compared to combining all of these strips together, right? So the next step is to draw again the beam in between these edges to control the punching. You can also increase the thickness, but you can go for the 24 or 30 inches, but that will be not correct because it is just a 3-story building, right? If you, the client and the architect are okay with increase in the thickness, we can go for it. And again, you have to define the beam, right? And this time the depth of the beam should be 18 inches, and we will take the width as 12 inches because the thickness of the footing is 18 inches, and we will take the width as a 12, right? And all of the properties are the same, which I've explained previously. And we have to draw the beams in between the edges, between the columns, to control the punching, right? So this is how you will, let me show the extrude view. Or there is also beam, so you can draw the beam in between the columns, right? So this will control the punching issue for you, and then you can design your auxiliary footing, combined footing very easily. So now this is the model, right? If I show the extruded view, so now these are the beams which I have drawn at the periphery to control the punching, not to increase the thickness of the footing. Now if I click on the punching, so there is no punching issue at the edges, and the interior punching has already been controlled by the thickness, 18 inches thickness of the footing, right? So this is how you will design and decide the combined footing. And we have already checked the demand to capacity ratio, and we have the issues, and we solved it using the strap beam. The next is the reinforcement of the footing for the combined footing, which is as per ACA 31814, that the design and detailing of the combined footing and made footing shall be in accordance with this section applicable provision of chapter number 8. And chapter number 8 is the two-way slab chapter, which means that all the equations and formulas and limitations of the two-way slab is applicable on the combined footing as well as on the mat footing, right? So again, we will first of all check for the minimum reinforcement using the ACI table 8.6.1, which is for the non-pre-stressed two-way slabs. So in our case, the FY is still the 60,000 PSI, and H is 18 inches. So if you use this, the 60,000 and equal to greater than, so these two equations are applicable. So if you calculate using these equation by putting all of these values, which is 18 is the thickness of the footing, and 12 is the strip per strip length, which is 12 inches, and you calculate is 0.39 inch square per foot, and from the other equation it comes out to be 0.3. So this much minimum reinforcement you should provide to the combined footing. All right, so let us go towards the save and check first of all the pattern and behavior of the footing for the bottom, which is very obvious that it will not require any reinforcement at this portion because the columns are in here, and we have provided much larger footing for the transformation of the load into the soil, right? So there you can see this behavior is very accurate because there is no need of the positive reinforcement in the one direction, which is this direction, but in the short direction, there is a need in all of the footing, which I've explained previously that in the short direction, the bending moment is more. So that's why this direction 2 is actually the short direction, which is the y direction, and it requires reinforcement all around the footing. So let us go towards the design and let us use number 6 bar at the rate 12 from center to center, and let us see what does it say. It means that it will work for the middle strip, middle portion, but it is not working for the outer edges, right? So we will go towards the 6 inches. Now you can see that this is working from this footing for this. You will see if you working a practical procedure and in consultancy, normally you will ignore these type of reinforcement. You can see this is very much less. It is 0.03 inch square per foot. So if I calculate the spacing required by this much reinforcement, it is very less, and normally it is ignored by the designers. So if I use number 4 bar and it is divided by 0.03, right, and if I multiply with 12 to convert it into inches, so if you provide number 4 bar at the rate 80 inches, which is very less reinforcement, so normally these reinforcement has been normally ignored, right? Similarly, from here it is 0.05 and it is 0.01. So these reinforcements can be ignored because these are very less, and we are already designed it with the factor load and too much safety. So you can ignore these reinforcements in your design. And similarly, in the other direction, this is the direction 1 bottom reinforcement. So again, the interior one is working with the number 6 at the 6 inches, but the outer one is not working because of the unbalanced moment from coming from the earthquake, and these are the at the edges. So you can try with 3 inches, and normally the reinforcement or the footing for the 3-story building, we provide the strip footing. But for the training purpose and for the understanding purpose, we move towards the combined footing, right? So if I check the reinforcement, still it's asking about too much large reinforcements at the bottom. So you can increase the thickness or decrease the spacing of the footing, right? So the top reinforcement, if I use number 6 bar and if I go for the 12 inches, so it is not working, right? So you have to decrease, because I have designed this structure with using the UBC load combinations and UBC earthquake, because some of the students, they are using ACI code, but they are using the combination of the ACI, and they say that we are using building code of Pakistan, which is not correct. You have to use the earthquake load combination of UBC and earthquake definition of UBC, and you can use the design procedure of ACI, not the load combination of ACI. Right, so we will go for the 6 inches, and it is still asking about the some reinforcement at the top of, because if you make the strip, so the reinforcement will be reduced significantly. Right, so we will go for the 3 inches, and you can see it is working for the interior in this direction, and for the other direction it is also working in 3 inches. And if you click on the 6, so it is also working in 6 direction for the interior one, right? So sometimes you have to neglect some of the reinforcement shown by the softwares, right? Because I have already explained that it go to the nonlinear analysis, and we assume or we perform all of our designs in the ETABs or manually as a linear elastic analysis, and it goes towards the nonlinear analysis, right? So this is the design in which for the bottom we will use number 6 bar at the rate 6 inches center to center. This is for the interior. And bottom, we will use number 6 bar at the rate 3 inches. Some of them, the students might say it is very too much reinforcement, but this is not too much reinforcement, because we are limiting ourselves to a very small strip, which is 5 feet into 14 feet. So if you provide strip, overall strip, so it will be working with number 4 bar, right? So we have selected this just for the demonstration purpose and for the training purpose. We will use number 6 bar at the rate 6 inches center to center. This is for the direction 2, which is the direction 1, which is the longer direction, and the top, we will use number 6 bar at the rate 3 inches center to center, direction 2, which is the short direction. This is the long direction, that is the short direction, right? And for the, this is all for the exterior. I'm talking about the exterior, and you have seen that for the interior, we will use all top number 6 bar at the rate 6 inches center to center. It was working at 6 inches for the both the direction in the interior side, right? So this is how you will, this is for the longer direction and this is for the shorter direction. In the interior, it was working with number 6 inch center to center for both the direction. For the exterior, it is not working, so we have selected this much reinforcement. Right, so if you calculate this reinforcement, it will be very much less, because you can see that this is a very sufficient reinforcement required by the footing, because it is 3-story commercial building, and it is located in zone 3, and the soil type is SD, so it depends a lot of on a lot of parameters, right? And the load combinations are UDC 97. So this is how you will design the combined footing in SAF, and you can design your any type of combined footing as per your requirement for the 2-story, 3-story. And if you go above the 3 stories, combined footing is not applicable, then you have to go for the strap footing, or you have, if the soil is very loose, you may go towards the raft as well. The next is the maximum spacing of reinforcement, which is same for all of the 2 slabs or footings. And similarly, in our case, it is thickness is 18 inches and the maximum spacing is 36 or 18. And this is the governing one. And we have provided 6 inches and 3 inches. And we have satisfied this requirement of ECI as well, right? So the next one is again the design of the strap beam. And I will be doing it very quickly, because we have explained it in detail in the previous session, that what we have provided the strap beam, and then you have to again design the strap beam. Right? Again, you have to design the, let me right click on this portion. So this is the dimension, this is 12 feet and 18 inches, which is the depth. So longitudinal reinforcement for the top at the support is 0.69, so we can take 0.7, and at the bottom it is 0.85, right? And the governing one is the now in here there is more reinforcement, so let us check this. So the top reinforcement is the maximum reinforcement is 1.98, and at the bottom it is 0.5, and here it was 0.8. We will take 0.9 and 1.98. And similarly for the transverse, it is asking about 0.63, 0.3, and we will take 0.62 inch square per foot as a maximum value. Because in here it is 0.12. You can also provide in variable and variation, but for the simplicity, I will recommend you to take a single value. It is 0.62. Right? So for the bottom, this comes out to be 0.9 inch square, and the minimum that governs for this beam is 0.63, and we have provided 0.9, so we are on the safe side. Let us go quickly for the maximum limit So we have the idea. So if you using this equation and the D is 15.75 and width is 12, so the maximum reinforcement you can provide for the strap beam in this combined footing is 2.6 inch square, right? So the lower limit is 0.63 and the upper limit is 2.6. So we are providing 0.9, so we are on the safe side. Right? Similar for the top, it is 1.98 inch square and the limit is 2.6 and we are providing 1.98, so we are on the safe side. So now you can use the bars. For example, if I use number 4, number 6 bar, and if I divide it with the 0.9, if I divide 0.9 by 0.44, it comes out to be 2 bars. So you have to go for the 3 bars because it is slightly greater than 2. You can also go for the combination with the 2 number 6 bar and 1 number 4 bar, right? So we will using 2 number 6 bar and 1 number 4 bar, so it will fulfill the requirement of the beam. And similar for the top bar, it is 1.98 and it will divide it by the area of the bar, which is 0.44. It comes out to be 4.5. We will use 5 bars because the negative demand will be more at the footing because of the unbalanced moment coming from the earthquake. So we will be using 5 number 6 bars at the support, and we will be using 2 number 6 bar plus 1 number 4 bar. Right? This is the made, and this is the right. So the reinforcement required at the mid for the top and bottom, let us check it. Example, let's go for the tuner and click on OK. So at the mid, the top is 0.2 and at the support the bottom is 0.4. So it is 0.2 and 0.4. So if you divide 0.2 by 0.44, so it is asking 0.45. So you cannot continue 0.45 bars or 1 bar. You have to go for the 2 bars. And for the bottom, it is 0.4 and we have to divide it 0.44. It is asking again with the 1 bar, so you cannot make continue bar as 1. At least 2 bars should be continuous. So we'll be continuing, right? So let us move this. So the bottom will be equal to 2 number 6 bar continue and top equal to 2 number 6 bar. Right, so this is how you will decide about the continuous and non-continuous bars. Right, so this is the design for the longitudinal. So let us go towards the design of the shear for the beam, in which the software has given us maximum value of 0.62 inch square per foot. Right, so if you calculate the spacing from it, so if you use number 1 bar, number 3 bar, if you divide by 0.62 and you multiply with 12, and it is 2.1, which is very less. So we'll change the bar size and we will use number 4 bar, and it is 3.8, which is correct, right? So we'll be using number 4 bar at the rate 3.5 inches center to center, right? So these are the minimum criteria, and it is not governing. This is governing. So we'll use number 4 bar at the rate 3.5 inches center to center, right? So this was the whole story about the design of the combined footing with the design of the strap footing with the combination of the combined footing. And I think this session is over, this Zoom. So I will end this session and I will generate another link so we can have our question answer session.